Hello, welcome back. So we are in now the third section of solving quadratic equations. We started out with solving by graphing, and then we finished up solving by factoring in class. And so now we're going to move on to the next section. And actually, this section of 9.1 is not really about solving quite yet. It's just the prep work so that we can solve by another method. And so the title of section 9.1 is Properties of Radicals. Okay? And you're like, Bacham, what is a radical? Let me tell you. Okay? So remember, you've probably seen something like this before, right? The square root of 3. That is a radical. Okay? And specifically, we said that 3 is what we called the radicand with a D. And then that root sign, that was what we called the radical sign. So what we're going to be talking about are properties about numbers of roots. Okay, specifically square roots. We'll look at what happens if it's not a square root in class, but we're mainly focused here on square roots. Okay, and also understand that the square root of 3 is not equivalent to 3. So let me get a calculator. Hold on, I gotta find one. Found it. Okay. Remember that if you have the square root of 3, that's like 1.73. That means that if we take that number right there and you square it, that number gets you back to 3, right? That's the idea of an inverse, okay? So we talked about inverses with addition and subtraction, but the inverse of a square root is a square. And conversely, the inverse of a square is a square root. Okay, so that's going to be important for us to kind of have in mind. But mainly, just understand that the square root of 3 is equal to 1.73, and 3 is equal to 3. So those are not equivalent things. A lot of people think they're equivalent because there's the same number, but it's not, okay? The square root is an actual operation that we have to consider, okay? And so the goal of this section, okay, by the end, we're going to be able to simplify an equation like 7 divided by 2 square root 3. And you're like, whoa, Bacham, I don't even know what to do with that. And I'm like, yeah, you don't. And we're going to learn. Okay? And so let's just start off simple. Okay? If I asked you what the square root of 25 was, you would probably, hopefully, easily be able to tell me that it was 5. That's what I would hope, okay? But I want you to start thinking about roots in just a little bit differently, okay? We're going to make what's called a factor tree. And if I remember correctly, you guys have made factor trees before, so this shouldn't be new. But if it is, they look like this. You take 25 and you break 25 down into all of its prime factors. And 25 breaks down into 5 and 5, and then you can't break down 5 anymore, okay? And so a really key thing for this section is understanding that you could also write the square root of 25 as 5 times 5, okay? And so what you have here now is that's also the same thing as saying 5 squared, right? And then you also know that a square root undoes a square because they are inverses, okay? Like, and if you don't believe me, you could go to your calculator and you could do the square root of 5 squared, and they basically undo each other, okay? And so what we're going to be looking at in this section is seeing, okay, when I have a pair of something underneath a root sign, I can pull it out of the root sign, just one of them. Okay, and that's going to be way clearer in this next example that I got. All right, but so that's just very simple. You're probably like, why did we do all that work? It's obviously 5. Here's why. Let's look at example 1. Okay, example 1, we need to simplify the square root of 108. Okay, And so if we go to our calculator and we plug in the square root of 108, we get a decimal. Ms. Baucom doesn't like decimals. Ms. Baucom likes exact answers. She's a mathematician. She likes exact answers. Engineers love estimations. I am not an engineer. I'm a mathematician. So we need to simplify this. And so we're going to use this idea of a factor tree to do so. Okay, so we're going to come off to the side. And we're going to say, okay, how does 108 break down? And it breaks down several ways. And you could do this completely differently than me and still get the same answer as me. I like to break 108. I like to start with 2 sometimes, right? Because 2 divides everything that's even. So this breaks down into 2 and 54. The 2 is, you're done with it. I like to underline them when I'm finished so I know that I'm finished with them. But 54 breaks down into 2 and 27. And similarly, I'm done with that 2, so I can stop. 27 breaks down into 9 and 3, and I can be done with that 3, but 9 breaks down into 3 and 3. Okay, so what we have done is we've just broken down 108 into all of its prime factors. Okay, and so we can say, well, the square root of 108 is the same thing as the square root of 2 2's, so 2 times 2, okay? And then I've got 1, 2, 3. I've got 3 times 3 times 3. Okay, so if you go to your calculator, you can always double check it. You can go 2 times 2 times 3 times 3 times 3, and you get 108. Okay, so we've just broken them down. We haven't changed anything. We've just broken down what our number actually is, okay? And now, okay, well, if we've got a pair of something that's like squaring it, so we've got a pair of 2's and a pair of 3's, and then we've got this 3 that's all by itself. And so what this means is that, well, if we've got a pair of 2's, then the square root undoes that, so you've got a 2. And then you've also got a 3 that can come to the outside, so you bring just one of them along, right? If I told you 2 times 2, you would say 4, and the square root of 4 is just 2. Okay, that's why I'm only bringing out one of them, all right? And then you're still left with the square root because you still have this little 3 underneath. It has to stay behind. It doesn't have a friend. Poor little 3. And then the last thing to do here would be to multiply the 2 and the 3 to be 6 root 3, and then that's where you would stop. And the cool thing about this is you can check it in your calculator, okay? We know we've got the square root of 108. And then if we did 6 square root 3, that's where you'd be as well, and they're equivalent. That's what you want to happen. So that's nice, okay? So now let's throw some variables in there. What if I gave you in example 2 here? What if I gave you simplify the square root of 9x to the third, okay? Now, you could come make a factor tree for 9, or you probably, hopefully, understand that 9 is just 3 times 3, okay? And then we've got x cubed, and so we're going to treat it just like we would any other number, and saying that x cubed, well, that's the same thing as x times x times x if we were to expand it, okay? And so we can circle our pairs because if we have a pair of something, that means that the square root's going to undo that power of 2. So we can take a 3 out, we can take an x out, and then left underneath we still have the square root of x. And that's how we leave it. We can't do anything else. I know it doesn't look super pretty, but you can't do anything else. You just leave it right there. Okay? All right. Let's now look at what happens if we've got a division. Okay, so example 3. Let's say we had the square root of 15 divided by 64x squared. Okay, well, there's this really, really smart old dead guy that figured out that this is the same thing as doing the square root of 15 divided by the square root of 64x squared. Okay? And so then you're probably seeing, okay, well, the square 15 breaks down into 3 times 5. And 64, like if you were to do a factor tree of 64, you could do like, 2 and 32, or you could notice that it breaks down to 8 and 8. And you could continue your factor tree because obviously 8 and 8 is not prime. But as soon as you have a pair of something, you can stop. Okay? So we could say that 64 is the same thing as 8 times x times x. All right? You could say lots of things actually, but mainly that one. Okay? So that's nice. And so then now you have a pair of 8s and you have a pair of x's. Okay? And so we can't simplify anything in the numerator there, so that's just going to stay the square root of 15. But then on the bottom, we can take an 8 out, we can take an x out, and then we don't have anything left underneath the square root, so we don't need to write one. Okay? And this one actually works out really, really nicely. Whenever you have fractions and radicals together, they're unhappy. They're like oil and water. They don't mix very, very well. Okay? And a prime example of that is actually what we're going to do next here in example 4. Okay? And so here in example 4, I want us to simplify the square root of, let's do 5 divided by 3n. Okay? And so the really old dead guy said, well, that's the same thing as the square root of 5 divided by the square root of 3n. And you're like, well, Bauckham, you can't do anything there, right? Okay. Well, if you've got the square root of 5 divided by the square root of 3n, it is unhappy. And it is unhappy because there is a radical in the denominator. Radicals in the denominator are bad. They're bad luck. They're not good. So we need to make the denominator not have a root sign, just like we did up here. This one was easier because it simplified. It was a perfect square. But now you've got this term down here. It's unhappy because of the radical in the denominator. So we have to get rid of it, okay? And we're going to get rid of it by multiplying it. Well, so let's think about this. What gets rid of a radical? Well, if you have a square root, a square undoes it, right? So if we could make what was underneath squared, then it would work. Okay, well, if we're going to write what's underneath as squared, then it's got to be multiplied by the same thing, right? So if you multiply it by itself, that's cool. We can do whatever we want as long as whatever we do to the bottom, we must do to the top. Now, if you're confused on how I got there, watch what's going to happen. Okay? Now, about the same time that the old dead guys figured out that this works is the same time that the old dead guys also said, well, if you have a radical times another radical, that's the same thing as the radical times whatever's underneath. Okay, those two things are equivalent. You can do that. You can go inside and outside of a radical like that. And then on the bottom here we have, well, you could say that 3n and 3n, that's the same thing as 3n quantity squared, right? There's two of them. All right. And then if we simplify this numerator here, 5 times 3 is 15n. And then the square and the square root go away, and you're just left with 3n. And that's okay. It's okay to have a 3n in the denominator, and it is okay to have a radical in the numerator. What is not okay is when you have a radical in the denominator. This process, by the way, is called rationalizing the denominator. Okay? When you rationalize the denominator, basically what you're doing is getting rid of a radical in the denominator. Okay? That is a very important process that you're going to need to know how to do in geometry. So they will teach it again to you in geometry, but it would be really helpful if you knew kind of going into it what you were getting into. Okay? And we're going to continue this process of rationalizing the denominator here in example 5. It's our last example. It's a bit more involved, but we'll be okay. Okay? We're going to go back to our goal. And our goal was to simplify 7 divided by 2 minus the square root of 3. Okay? And you're probably thinking, all right, well, okay, I see kind of we got a radical down there. And so we're going to have to get rid of that square root of 3. But the reason why this one is a little bit more involved is because now this is a binomial on the bottom. You've got a 2 and then a minus. Okay, so we're going to deal with it a little bit differently. Okay, now this is one of those things where Miss Baucom is going to do something, and I don't expect you to have come up with this on your own. This is just something that I'm going to tell you, and I want you to watch how it works and then see the pattern. Okay, so we know in order to get rid of a square root, we're going to need that same thing again, right? That the idea of something being squared is that it's a power of 2, and then a square root can undo it. So we're going to see a square root of 3, but because we have this 2 right here, okay, we have to have both of those things present. And then we need things to cancel out. So instead of a minus sign, I'm going to multiply it by a positive, okay? And then whatever we do to the bottom, we must do to the top. Now, I know what you're thinking. You're like, Baucom, you have just done gypsy magic. How did you do that? That's what I'm telling you, okay? This process here, this is called a conjugate. Okay, and you'll hear that word again in algebra. This is called a conjugate. And a conjugate is basically what could you multiply it by to get rid of a root? Watch how this works. Okay, if we're going to multiply across here, that's like 7 times 2, which is equal to 14. And then 7 times the square root of 3 is just that. There's nothing you can do. You cannot call that the square root of 21. You just leave it as 7 square root of 3. Okay? And then on the bottom, okay, now we've got 2 binomials and we're going to have to FOIL. So we've got 2 times 2, which is 4. 2 times the square root of 3, which is positive 2 square root 3. Negative root 3 times 2, which is negative 2 square root 3. And then negative root 3 times a positive. All right, well, negative and positive create a negative. And then when you have the square root of 3 times the square root of 3, that's the same thing as the square root of 3 times the square root of 3, like that. Okay? And then there's a pair. That's good. You want that to happen. Watch what's about to happen here. The numerator has to stay the same. There's nothing that you can do up there. Okay? But look at this bottom. Positive 2 root 3 minus 2 root 3, that goes away. Okay? And so now we're just left with 4 and then minus, and then the 3 and the 3 come outside just to be a 3. All right? And then that simplifies even more to 14 plus the 7 root 3 divided by 1. And you could write the divided by 1, or you don't really need the 1 on the denominator, so your answer here is just 14 plus 7 root 3. So what that means is that 7 divided by 2 minus the square root of 3 is equivalent to 14 plus 7 times the square root of 3. And if you don't believe me, you could plug it into your calculator. Just make sure when you do that you put parentheses around that right there. Okay? Again, this is called rationalizing the denominator. All right? Lots of big steps that we took just now. So I would encourage you to think about the questions that you have, come into class ready to ask them, and then we're going to talk even more about this process and a few more extensions of some thoughts here. So good luck, get started on your homework, and I'll see you in class.